All right, hello everyone. Welcome to our third tutorial. So today we're going to go over generalized regression, nonlinear regression. I'm going to talk about a couple of other topics that you guys are going to learn about in the future, very briefly, and touch upon them. And then if we have time, I'll hopefully get into multi-regression. So just as a refresher from last week, so I know the professor started classification naive Bayes. What I'm going to do is I'm going to hold off on presenting that until next week and spend two of these tutorials on regression, just because I think regression is very, very powerful. It's very important and it's commonly used, but conceptually the professor could explain it in only like one large lecture series instead of multiple. And I also think that classification makes a lot more sense once you see multiple classification techniques. So I think it'll be presented better next week. So the other thing is, like, I honestly wish I could spend even more time on regression for how important it is, but I'm going to try and squeeze in a lot of various methods in this tutorial, and then it's up to you guys to visualize your data, see them in the project, and then identify what type of regression to use if you're doing regression. So one thing that we're going to learn, as I mentioned in the first tutorial and in the second, we must always learn to visualize our data. And we can make assumptions on what our data looks like. After we visualize it, we can validate those assumptions and then use the correct algorithm. So for linear regression, as you learned in class, there must be a linear relationship between the x and y, or the feature that you're using, and the predicted value. So if it's not linear, we learned something in class as well that we can apply. Do you guys remember what that is? You guys could use a log transform or another type of transform. So if we go to the regression page on the course notes, there are a bunch of transforms that we can use. Sorry, it's taking a little bit to load. There are a bunch of transforms that we can use. So depending on what your model looks like, you can apply a log transform, square root. You can take the reciprocal. You can transform your data to look linear and then fit a linear line. And that's kind of what the professor said. So based on the last week's challenge, did any of you guys try that example that I gave? You guys look at it? Okay. So what I'm going to do here is I'm going to present the results of that, and the biggest takeaway that we're going to learn is that you should still always visualize your data even after you apply a transform. So what I'm going to do is I'm going to load that log regression example that I had yesterday. So the feature that we're using is the size of a property. It's like a property of a house or a home, and the price of the property, and this is, I guess, in millions of dollars. So last week I actually made a mistake last week where I was having trouble plotting the data and it was giving me a weird error. So there's this function that you can use that's data.columns, and what you can do in data.columns is you can change the column names. So here, size of property, that's a very long name to use. So for simplicity, last week I just tried to use size and price. So if we change the data.columns and we print the first 5 data points again, we can see here the name of the column changed to size, and the price I just named price. But the problem was, usually when you index a column on a data frame, you can just do the dot and then the name of that column. But what I learned after the tutorial was that size is already a function that Pandas has. So if you do data.size, it will actually give you the length of the data, not the actual column name, which is interesting. So the other way to index that we learned is you can index this way. You can index this way, and it gives you the full. But I generally like using the dot because it's shorter. But I guess I learned that it will give you an error if you use size. So instead, I name my column property size. It's a little bit more clear than just size, and I can index it the same way. So here we can do a plot of the data, and this is kind of the data that is given to us. And we can see here that there's a very sharp increase, and then it kind of peters off. And maybe if you think about it conceptually in a real world situation, you can think about prices being might have a steep price based on their size, but then at a certain point when the properties get very large, let's say it's out in the country, maybe the price kind of steeps off and there's another subcategory. So I mean, we could cluster and we can do various things, but let's say if we wanted to fit a line that looked like this, one way to do it is to apply a log transform and then apply a linear model to it. But one thing that I'm going to talk to you guys about now is a thing called cross-validation. So I don't think Professor Golab touched on it, did he? He might have mentioned it in the first lecture, but cross-validation is a very important technique. The method that I'm doing it here in this tutorial is not the method that you would use for your projects. You guys are going to learn how to properly do cross-validation and learn something called k-means validation, or sorry, k-folds validation. But today I'm just going to explain the idea conceptually. So if you have a data set and you try and apply a machine learning model to it, the problem is the model might overfit, meaning that it will memorize what the data looks like in terms of classification, or in terms of linear regression, it will try and fit a too good curve to the data that it will not generalize very well. And you'll see in this tutorial kind of what that'll look like when I say not generalize well. What that means is that it will try and build a very, very complicated relationship that will touch every single data point. So your error will be very, very low. But if you deal with real world data, it won't actually work well with new data. So the way to combat that is you split your data set up into two halves. You have a training set and you have a testing set. So the way to do it is you randomly shuffle your data and then you select a percentage of the data to build your model with, and then you select a percentage of the data to test your model with. And when you build your model, the model never sees the testing data. So what I'm going to do is I have some code here that will shuffle it'll shuffle the data, and then it'll split it into a training and testing set. And for just this tutorial, I use 25% to test on and 75% to train on. People use 70-30, you can use any amount. Later we'll learn k-means, so instead of just splitting it into two groups, k-folds, we'll split it into k different folds. So maybe it could be 3, generally people use 10. So what it'll do is you'll have 1/10 of the data, 1/10, 1/10, 1/10, and then you will train on 9 out of 10 of them, and then test on the 1/10. And you'll train on another 9 out of 10, and then you'll do that 10 times, and it'll take the average score. And that's a better way to do cross-validation. But I'm just going to show you intuitively what it looks like here. So one more thing that I'm going to talk about is the idea of a random seed. So when you use Python and use computers in general, you can't generate truly random numbers. A lot of the number generators actually start with a seed number and give you pseudo-random numbers. And to create reproducible research, so when you run an algorithm, if I want to run it and it looks the same on everyone's computer, you should set a seed number. So when you set a seed number, when people randomly generate on another computer, it will use the same methodology based off that seed. And I'm not going to explain how random numbers are generated, but you should always set a seed when you're using the random function in NumPy. So if I run my code, I just want to explain the graph first. So what it did is it split the data up into two sets. In blue, you can see the training, and in red, you can see the testing. So what it did is it just randomly shuffled the data, and then it's randomly selected 25% to test, and I just plotted that in red. And then it's used the other 75% to train on. So when the algorithm tries to build a model, it will only build it on the blue points. And then when I do when I check my residuals and my error, I will check it on the red points. And that's kind of the point of cross-validation, is that you test it on data. And I'll show you in another example kind of what, if you don't do that, the error that you'll have. And I guess what we can do is we can just take a quick screenshot. I just want to show you what random seed will do. Sorry, my computer's running slow today. Yeah, this is pretty bad. Sorry. Actually, what we can do is we can just save the image. We can just save the image, I guess. So if we run a different seed number here, we can see here that the red dots, they kind of change. So it randomly selected the data. And you can see the problem with just doing it this method is in this case, when the random seed is 2, it only has 2 of the testing data up here. It's possible, since it's random, that you select none of the data up here. So that's why we use k-mean, or k-folds, because we split the data 10 times, or k number of times, and we average the score then. So you can see what it'll look like if you change the seed to 3. It just generates it just shuffles the data differently. So you can use any number you want for your seed, but we'll just keep it for 3 for now. So next what I'm going to do is I'm going to create a linear model, just try and fit a simple line using the simple linear regression in scikit-learn, and we're going to do it on the training data, and I'm just going to print the coefficients. But when I do my residual sum of squares, I do it off the predicted from the testing set. So you see when I run the fit, I run the fit on the training or the blue data. When I measure my error, the residual sum of squares, I do it off the testing set. So I'm going to just create a scatter plot, and we're going to look at the linear fit. You can see that this is a very, very poor fit, right? This is not what you'd want to be doing if this is the real world, mostly because it doesn't generalize well for an increase here. So if you look at the data, you can make an assumption. So there are all those different transforms. And the methodology to find the right transform is kind of trial and error. You take a look at your data, you make a hypothesis on what you think an appropriate transform will be, and then you fit a linear line, and you can inspect it visually, or you can look at the residuals, or you can just use the sum of squares error. And again, when you do that, make sure that you split your data into training or testing, or use some form of cross-validation, which you guys will learn soon. But if I look at the data, I can see that it could be, you could use the it could be like a logarithmic scale, because it increases very, very quickly, like more than a square root, and then it kind of tapers off. So my idea is, hey, we could maybe run a log transform, and then be able to fit a line. So in my so here I basically apply a log transform. So I use the map function. So I take the training data dot property size, right, which is my x, and what map does is it applies the function inside of map to every single data point in that list. So I'm logging the property size. That's what the map function is doing, and it's a quick way that you can apply. Like sometimes you'd want to maybe use like a for loop or something and iterate on every single data point. NumPy and Pandas already has a function to do that for you. That is a lot faster. So if you use map, it'll give you the log, and then I also do that, and then I also reshape it because again we need to reshape whenever we use linear regression, as I showed last week. And then what I end up doing is I create a new regression model, and then I use it the train after the log, and then I give it the y values. I also get the coefficients, and I calculate the residual sum of squares from the difference again of the testing set. And then I also plot it basically. And if we run the code, we can see here what it'll look like. So here I fit a linear model to this, but if we transform the data back, right, taking the exponent, it'll actually fit a really nice curve over here. And we'll see that if we look at the residual sum of squares, it actually decreased to be quite small. And you can actually visually see that it actually hits a lot of the data points. Maybe not down here with the smaller property prices, but it basically it's pretty centered, and it looks like a decent model visually. And if we look at the residual sum of squares, if we want to go one step further, we can take the residual plot and see that it's normally distributed. And if we compare it to the residual sum of squares here, it's a lot smaller, right? Which indicates to me that we've built a good model, right? Like this could be, like we could use this, right? But the answer is that we shouldn't just blindly apply a log transform. And as I said previously in the past 2 tutorials, we should always visualize our data. So I wanted to show you guys an example of why that's really important. And so now if we actually apply and plot the data after the transform, this is what we'll get. It literally says, I tricked you. So don't blindly, the point of this is don't just blindly apply a transform and not look at your data, because you can always have hidden insights after you apply the transform. So here, yes, it basically looks like a really nice, it's a little bit higher here, I guess, because of the way that the data was split. But you can see, yeah, we can fit a really nice linear model to the data, but there might be hidden insights. And I mean, I made up this data set, so I put the I tricked you. But in a real life data set, maybe it's cyclic. Maybe your data is cyclic, and then you can use like a cyclic model to model it instead of just a linear model. So it's very important that you always visualize your data in every step of the process. Especially after you build the models, visualize it. When you apply transforms, visualize it, because you never know what hidden insights you'll kind of find in your data. And hopefully this is like a fun example that will always remind you that I tricked you guys. So make sure you always plot your data. So now we're going to move on to more generalized linear models based off of the last tutorial. So we plotted of the first tutorial. So we plotted Anscombe's data set. Remember that, where the linear regression was the same, as well as the mean, standard deviation, a lot of the summary statistics were the same. Today what we're going to do is, instead of fitting just a linear line, we're going to generalize for all of those data sets, and we're going to fit a better model, regression model to it. So in our first case, when we looked at the data, it was, I guess we can create a scatter plot of it. We can see here that this is obviously not linear. It looks kind of quadratic to me. It looks very quadratic, actually. So we're going to learn how to do curve fitting. So we're going to fit, let's say, in this example, a second order polynomial, mostly because it looks quadratic to me. So we can try out a second order polynomial. The way we can do that is we can use the polyfit function. This is from NumPy. So it fits a polynomial of degree 2. And you can fit any number polynomial to it. So if we run the code, basically what I do is I fit a polynomial, and then I plot the polynomial, and I plot the data. And we can see here it fits pretty nicely. You can also do linear regression, as I showed in the last week's tutorial, using a polynomial of fit 1, and it will just use like y equals mx plus b, which is obviously not good. If you look at the residuals, it won't be good. And you can even start using more than more than just a second order. So a third order here fits pretty well as well. So now that's the question: how do you know what order polynomial, or how complicated is a model that you're building based off your data? And I just want to take this same data set, and since this was generated by a statistician, I want to add a little bit of noise to it, so it'll look like what it'll look like. It'll look like a data set that you could see in real life. And adding noise can be created also using the random function. So I get some noise, and then I basically just add the noise and multiply it by 3, just so we get some variability in our data. So instead of actually, I'm not going to fit the. Actually, I'll just plot it all. Actually, so what I do is I add some noise to the x, and we'll see what the noise looks like. And then I also fit a polynomial, the same polynomial to it. So here, this is what the noise added. It just created some variability in our data. And here I also fit a second order model to it. And you can see when you apply curve fitting, similar to linear regression, it will try and reduce the residual error, basically. So you can see that it fits kind of in the middle, and that's like a generalized way. If you know that your data is not linear, you can apply curve fitting and fit, for example, a polynomial to it. But the question is, can we improve this with more than just a second order polynomial? If we use a third, a fourth, a fifth order polynomial, will it fit better and reduce the error? Right? Because if it's more complicated, you might find some other trends in the data. So in this example, I use a polynomial with degree 5. And as we can see here, it looks generally the same, but you can see that it's a little bit steeper here, and it fits the data better, and the residual sum of squares error goes down. So up here, it was around 0.12, and if we apply a fifth order, you get a 0.09. Okay, so that makes me wonder, like, oh, we used 2, we used 5. Maybe we can fit a really high order polynomial and get a really low error, right? That makes sense. If we fit a very high order polynomial, let's say of degree 10, we can see that the residual sum of squares error goes to 0. And when we look at the residual sum of squares error here, and we look at the model that we fit, it's very complicated. We can see that with the 10th order polynomial, it goes up and down, up and down, up and down. But the error is still 0. But here we can see that it's overfitting. That's what I mean by overfitting. So here we can see that it's fitting well. If we just run, let's say, an order of degree 1, we can see that it's underfitting, that the model is not complicated enough. Here, if we use a fifth order polynomial, we can see that it appears to be fitting pretty well. But if we look at a very high order polynomial of 10, we're overfitting. And what that means is, let's say, for example, it's a little bit hard to see the numbers, but if we had the x value of 5, if we use our model, it will predict that the y value will be around minus like 45, when really you would expect it to be above 0. So, but if you apply that, say, if you look at 5 over here, you can see that this model will predict it to be around 3, between 3 and 4, or whatever. So we need to be careful for overfitting, and the way to prevent overfitting is to only train a model off of a subset of the data, as we saw up top, using cross-validation. So you use a subset, you build a model, and you test it on data that the model has not seen. So here, it won't try and touch every single point. So if there's a point here, we would see a huge error, and we would know that the model is incorrect and it's overfitting. And while this may seem obvious, because we're applying the data here, and we're only dealing with one feature and one predicted value, when you start dealing with a large set of inputs or a large set of features, you're not going to plot your model on every single data point, or you could, but it becomes very difficult in n dimensions to visualize. So the way to automatically solve for that is using cross-validation, which you'll learn. So I just wanted to give the intuition here, because it comes again when we start doing classification. And the professor will go over it. I just wanted to kind of show you the dangers of just using a metric such as residual sum of squares. You can say, oh, my model is great, but in a real-world situation, when real data comes in, this model wouldn't perform very well because it doesn't generalize. So next, why don't we work with the next set of data in Anscombe set. So here we saw that it was generally linear, but there is one outlier, and that one outlier caused that linear model to be incorrect, and it had a great effect on the residual sum. So what are methods that we can do to avoid that? One, we can manually find outliers. At the end of the course, after you learn distance measurements, Professor Golab will teach you how to do outlier detection. There are many different ways you can do you can use to remove outliers. But one thing that I wanted to show is sometimes there are functions that already have what you're looking for documented on scikit-learn. So if you read the linear models documentation for scikit-learn, it'll explain ordinary least squares, and it'll start showing different examples. So in this example, there's a thing called RANSAC, which is random sample consensus. So it's an algorithm that helps you detect outliers. And usually in the documentation, if you click this example, it'll give you the code that I used to generate it. And I'll show you in our example how they use that. So it helps you have the inliers, helps you have the outliers, and then it fits a RANSAC regression to the inliers compared to the linear regression of the outliers. And if we go back to our example, I just used the code from there and use the same RANSAC regression. RANSAC regressor, and fit a model to our data. So here you can see that we fit that red line, which is our RANSAC regression. we can see what a general linear regression would have had because of that outlier. And it also, I segregated the inliers and outliers, and the code for that is here. So the next thing we can look at is that last set of data where we see all of the values basically with an x, and then we have one outlier. And we can try and fit a linear model to this, but I argue that there, A, could be not enough data, as in we didn't collect data with multiple values of x, or that this is just an outlier, and this is actually just univariate data. So we should maybe just look at the y values and ignore the x values because they're all the same. So the point of this example is to show sometimes there isn't a linear regression that you can fit to a data set. Maybe your data is not good enough. Maybe your data, x is not dependent on y, right? If these are the cases, then you shouldn't run a linear regression. So make sure you always visualize your data and you understand kind of what it looks like. I wish I had enough time to go over all the different types of regression. There's so many, and they're all very powerful and useful in many different cases. So I put a bunch of examples here, mostly in scikit and then also in Statsmodels. And I'm just going to show the images of them very quickly. And you obviously don't need to know every single type of regression algorithm that exists, but knowing that they're there, and if you know that your data looks in this form, you can use this model. So next week, you guys are going to learn decision trees, entropy and decision trees. You can actually apply decision trees to regression. So once you learn decision trees, this will make a lot more sense, but it can fit very nonlinear and cyclical data by changing the number of estimators. You can also use nearest neighbor. When you learn distant measurements later in the course, you'll learn using nearest neighbors for classification. You can also use it for regression. So in this algorithm, it tries to find the closest points that are nearby and averages the distance between them and uses that as your prediction. And that could work as well in certain cases. There's support vector regression. You'll learn what support vector machines are. They're very useful for classification, but you can also apply to regression, and this will make more sense once you learn that. There's isotonic regression, which I really haven't used that much, but it also fits nonlinear data. By an isotonic fit, the stats model that we learned how to use last week. If you actually look at the examples, it has really good examples of regression. It explains the variables that we talked about last time, or the metrics, sorry, from linear regression. But in addition, it shows you how to fit cyclical data, and it also has, this is similar to the isotonic example, where you can fit different models, and it also shows you hypothesis testing and quite a few things you can do. So I have the link to that. There are also robust linear models that can work. There's also generalized linear models, and you can read through this. Generally, it all depends on your application and how important getting very good results are. Sometimes it's simple enough just to use simple curve fitting, but an example, if you're building, let's say, like a trading bot on the open stock market, you'd want like very, very good results, and you'd want a very robust model that prevents your overfitting and your underfitting. So later we'll learn about bias and variance error. So there are three types of error. One is bias, one is variance, and one is irreducible. The bias and the variance both relate to underfitting and overfitting. So you want to reduce that error, but you can't reduce all the error completely because we live in a real world where data is not always perfect. So depending on what your application is, there are really powerful statistics, and they're also weighted least squares. And these are, I guess, some examples that you can read through as well. And finally, there's also this is also a very powerful package. So it's least square minimization and curve fitting. I haven't really used it, but I've seen IPython notebooks that have used this in the past. There's, I guess I showed you guys ransack. So there are all these different methods for doing regression. What it really comes down to is plotting your data and understanding what your data looks like, and then trying to find the right algorithm to use. I have a bonus example here. Professor Golab talked about piecewise linear regression. You can also do piecewise. One method, so if your data set looks something like this, You can fit a linear line here, and you fit a linear line above. You can use this. I generally prefer to use the more robust regression examples, mostly because piecewise regression, if you do it manually, it becomes very cumbersome if you have more than one feature. But if you know, like in Professor Golab's example, let's say energy usage in the home, and you know that it would be based off different times, and there's a clear distinction on your data set. An easy way to do it is just subset your data, maybe into nighttime data and daytime data, and then build a linear model for each of those. But you can also use the optimize function to curve fit as well, and you can fit two sets of data, and you can also do it for nonlinear as well. And I found this code off of Stack Overflow. I just Google searched how to do it in Python, and kind of it gave me an example. So here it actually fits multiple curves, which is kind of cool. So that's there as well. I recommend mostly reading through the documentation here and trying to use more robust regression, especially when we get into a thing called multi-regression. So that's kind of what I had presented for non-linear regression and robust regression. The next thing I'm going to just touch on. So I mean, I wish I could spend more tutorials on regression, but we don't have the time. So I posted I have another notebook that goes over a thing called multi-regression. So we learned how to do non-linear regression for one feature, and we just plotted that on a scatter plot on an XY. When we deal with real-world data, you're dealing with more than one feature. And when you deal with more than one feature, you're doing a thing called multiple regression, or you're fitting multiple lines across multiple variables. And if you guys have taken, so first of all, this example is actually not created by me. It's created by guys at a company called Data Robot. And I took their example mostly because I tried to create my own, but this is probably one of my favorite tutorials that I've read through. And it actually deals with real world data, so I decided to present it here in the last like 10 minutes of this tutorial. So the intuition behind multi-regression is that you are actually fitting. So if you have 2 dimensions and you want to fit something to it, what do you fit on 2 dimensions? You fit a line. If you guys have taken linear algebra, if you have n dimensions, what do you fit? You fit a plane, right? You fit a plane on your data. So if you use linear regression across two features and you have one predicted, you're actually fitting a plane across that data set. And I'll show you what that looks like. So let's run all below. So this is what fitting a plane looks like. So in this example, it takes in a real-world data set from here. And actually, when you do pandas or pd.read CSV, you can actually put a link directly. And if the link is up and the data is on the internet, it can actually be downloaded. I generally like to download it locally, mostly because URLs change. But in this example that they use, this is an advertising data set. And if we look at the data set, we can look and we can see advertising. I think these are dollars spent maybe on TV, radio, newspaper. And then we can look at the sales, right? And let's say we wanted to build a predictive model for how we can increase sales using these sets of features, and we can see maybe which ones give us better sales: TV advertising, radio, or newspaper. And then you can figure out incrementally, if I put some more money, let's say in radio, my sales will increase, or figure that kind of out. And what you're actually doing is you're fitting a model that looks like this. So here they use beta as the coefficients, but you're fitting some scalar number multiplied by this feature plus some scalar number multiplied by this feature. So this is like y equals mx plus b if you ignore the radio on a line. But if you actually deal with it with 2 features, you're actually dealing with a plane. And here I tried to make it as 3D as possible. The white here are the points above the plane, the black are the points below, and the color of the plane is the actual sales. So obviously, as you spend more money in advertising, these sales increase, I guess, in this data set. And it appears to be pretty linear, and you fit a plane to the data. This only works if you're dealing with 2 dimensions, because if you're dealing with like 4, 5, 10-dimensional data, you can't visualize. It's very difficult to visualize. The way to visualize it is, as I showed in the first tutorial, where you make a scatter plot for each variable, and you understand that it's going to fit a plane in n dimensions. So it was hard to wrap my head around kind of what that looked like. Similar when you take linear algebra, understanding n-dimensional space versus 2 or 3. So this is what fitting a plane looks like. And you can actually, in the same way, use ordinary least squares to create a fit, and you can use the metrics on more than one feature. So here they use TV and radio, and you can fit a line, and as I showed you, that's what it looked like above. In this example, we also deal with categorical variables, and I just wanted to briefly touch on that. So we learned that there are different types of variables, right? There's numeric variables that are real numbers and are continuous, and there are categorical variables which are discrete, right? So for example, family history, it could be like, if you're like obesity, that could be like a BMI index. That's like a real world number. But something like family history, whether their family is present or not, is categorical. It has 1 or 2 different categories, like gender, for example, male, female, other, or the other ones. There's only a certain list that you can that you deal with. So when you deal with these kind of variables, there are different ways you can handle it. Mostly because you can't generally plot. You can't just apply linear regression to a categorical variable. The way that you can change from categorical to a numeric value is a thing called encoding. So, for example, if you had three categories, let's say gender, so you have male, you have female, and you have other, you could do something like make, for example, male 1, female 2, other 3. But then the problem with that is it creates a hierarchy where 2 is greater than 1 and 3 is greater than 2. So you might not be able to fit a model very well. So one way to do it is encoding the data by actually setting a new feature called male, and it'll be 1 or 0. Female, 1 or 0, and then other, 1 or 0. And do it that way. That way you can generally fit a line better. There are also many other ways you can encode, and the notes kind of go over that as well. So in this example, we load another data set, and then you can also group by certain things. So in this example, the categorical variables are the family history, so present and absent. One way you can do it is actually just take the mean, and as I said, there are natural ordering, so you can apply linear regression if you convert them to numeric. So in this example, there are natural ordering. So if they're absent, you can represent it by a 0. If they're present, you can represent it by a 1, and that's okay, because that makes sense. It's a binary variable, and then you can actually just use the categorical function, and it will actually just set to a 1 or 0, and it will fit a model. And I think there's an error. I'm just going to move on from here, mostly because we have 5 minutes. So in addition, there are other ways you can encode data, and you can also see the interaction between them. And if we go through the rest of the tutorial, it kind of just shows different methods you can apply to. I think there's probably an error on one of the variables, so I'll fix that when I get home. But in this example, you can just read through it. It's a little bit complicated in your example for your data set, but running multi-regression, the basic intuition is that you're fitting a plane, and they also show general linear models here. So I tried to fix most of the errors yesterday because I took it from their blog post, and some of their data sets, the URL changed, so I fixed it, but I guess there are some errors still in this document. But the main idea that I wanted to present is the idea of fitting a plane to a set of data. So if you have more than one feature, you would want to fit a plane, and you'd want to validate your assumptions. So for example, if one of your features is in this example like a polynomial, you wouldn't want to fit a linear line because it would generally underfit. So you'd want to fit a curve to it, but that becomes more increasingly difficult to do as you have more and more features. And if we apply what we learned in the tutorial that I just showed, if we have a data set that kind of looks like this, we can try and fit a linear model to this and get the same residual error as we would get as one of the other ones above, but it would be completely incorrect, even though that this data set is univariate. So what we would want to do is always make sure that you visualize your data, and that's kind of like the biggest takeaway that I wanted to present today. And again, just as a reminder, if we wanted to do it with multiple features, we can use Seaborn. We can use Seaborn, and we can use the grid plot. So if we go back, we have the example that I showed last time using the pair plot. So in this example, this is again a multi-variate data set. So there are different features here, and it plots each feature against each other. And then, so this is kind of what you'd want to do. So for example, in this case, we can see here that the data is pretty linear if you were to predict it. And the colors here are when we start getting into classification, but like here, this is very linear. In this example, maybe you could split it into each of the 3 different categories and then fit a linear line for each one. That might work better than just trying to fit a line. And this is very linear. So another thing that you can also do is a thing called feature selection. So when you build a model, just because you have like 100 different features doesn't mean you need to build a complicated algorithm that fits all of them. So you don't have to run regression on every single feature. What you can do is you can build a reduced model where you only use a certain set of features. And why would you do that? Again, to prevent overfitting. So as you have more and more features, your data set is more and more likely to overfit. So if you reduce the number of features that you use, you can also reduce your error, and it will work generally better in the real world because it will generalize better. So at the end of the day, when we start building models, there's a trade-off. There's a bias and variance trade-off where you're trying to fight from not underfitting, and you're also trying to fight not overfitting. And as the tutorials go on, I'll be able to show you kind of what that bias and variance trade-off looks like and how we can deal with it. You'll learn cross-validation. I just wanted to present all these techniques today, as long as give you examples of how to do robust regression and multi-regression. So in this example, if I wanted to, for example, do linear regression, and I had these 3 features to select the sepal length, since these 2 are more linear, they look more linear than this one, what I could actually do is just ignore this feature, the sepal width. So if we ignore the width and we just look at the petal length and the petal width, we can actually fit a plane in 2 dimensions, and that could generalize maybe better in the real world. And if you would test that using cross-validation. Same way in this example, these 2 are linear, so maybe we could use these 2 compared to the sepal width. So hopefully that gives you guys some intuition. Just to recap, always visualize your data. There will always be hidden insights that you'll find. I hope you guys liked that tutorial of the I tricked you. Hopefully it'll remind you that you should always visualize your data even after transforms, and hopefully the links will help generally with your regression. So just visualize your data, make assumptions, and then you'll be able to fit good linear models. So this is the last tutorial that I'll be presenting on regression. We'll be moving on to classification next week. Cool.